Hi again. So we have reached the exercise of the sliding window. So it's a very common and well-known exercise, and it's widely used in network. So we have an array A, which and a sliding window. So we have a set of elements and a width, so like a window, and we need to check for each window the maximum element. So we need to find an optimal way to get the maximum of each window. So we have an array A and we need to output an array B. So knowing that the elements, so if for example here we have 8 elements in the initial array, the output array is equal, so the length of this array is equal to the length of the first array minus the window. So we have here 5 elements because here we have 5 windows, and each window is equal to 3. So we need to find an optimal way. So so the optimal way is by using, of course, deques. So you can use it by using arrays. However, it will take too much complexity, and until at the end of the function we will find the complexity of the function. So we have a set of elements, and of course we will use deque. So in this deque, and let's see the example here. We have 1 3 minus 1 minus 3 5 3 6 7. So for the first 3 elements there's a special treatment because there's nothing before these 3 elements, so I need to check these 3 elements. However, we will do some tricks here. However, in the following windows, so we can either cap some of these elements or not, depending on the algorithm. So what we will do here, so in the deque we will save not the elements but the indices. Why we need to save the indices? Because when we reach here, for example, in one of these intermediate windows, for example, in the deque we could have some elements from the previous windows because we need to calculate the maximum. So the question that we ask is, how many elements should I remove from here to here? Sometimes, for example, here minus 3 is minimum, so I will not keep it because I have 5 here, so it's impossible to have it later on as a maximum. So I will not keep it, not here and nor here. So for that, sometimes I will not remove elements because they are already removed from the deque, and sometimes I need to remove 1, 2, or 3 elements, depends on the situation. So for that, in the deque, we have just the indices, the index of the elements in the original queue. So let's, for example, say that we have index 1, 2, and 3. So whenever I am treating a new window, forcibly I can remove or not the front element, and of course I will add the newly inserted elements in the deque because it could be a maximum later on. So for that, I can also remove some elements from here, because if, for example, I'm adding the fourth element and the fourth element is bigger than those elements, so I need to remove this one. So let's first repeat. So for the first part, we will do, for the first 3 elements, we will do a special case. So in order to keep the maximum, and for the resting windows, we will, of course, at all time insert from the rear part. However, I also can remove elements from the rear. So if the element in the array that I'm adding is greater than those elements here, I should remove them. And again, depending on the index and the window size, I can remove some of these elements if they are no more in the window. So I have kept the implementation, so let me remove the implementation of the maximum sliding window. So I have kept the solution of the deque. So you can go up to the previous exercise of the static implementation of a deque. You can find the link on the description of this video to check the implementation of a static deque. So I have also made a test, so it's the same one here. So I have an array of size 8, and then I have an array of b. However, b, it will not be of the size 8, it will be of size b 8 minus 3, which is equal to 5. So let's see what we will do in the sliding window. So we have an array A, the size of the array A and the window, and the size of B would be n minus w. So we'll use deque. So it's capital, I think, here. So deque is equal to create deque. So from here we need also integer I because we will need a loop and an element for the front and the rear elements. So for the first three elements, so for I equals 0, I less than w for the windows. So forcibly I will try to enqueue to insert this element in the rear. However, while inserting, I could also delete some of these elements. For example, if you go back here, whenever I'm enqueuing 1 and when I'm enqueuing 3, so forcibly 3 is maximum than 1, so I will not keep 1. So for that, I will do a loop, and as long as the deque is not empty, so not is empty a deque of q here, and we have the rear element that we just got it, so q address of e, and if, so as you remember in the deque we are having just indexes. So if the element that I will add is greater than the element in the deque, so here 3 is greater than 1, I will remove 1 because it will never be a maximum. So what I will do is that I will delete the rear before inserting the newest element, which is I, the index. So I will continuously delete, and then I will insert in the rear address of q, I will insert I. So this will be repeated 3 times just for the 3 elements. So if for example, I'm inserting the third element, maybe I can delete the first 2 elements. So this is just for the first window. So we are just 3 elements in the example. And then I will move on to the remaining windows. So I from W, and then I is less than n, I plus plus. So every time in each iteration, I will treat one element. So while treating, for example, here -3, should I add it to the deque or not? So it depends. Here it's too small because I have -1, so it will never be -3 for now, but it could be later on if, for example, you have here -3, -5, -6. So we should keep it. However, if it's maximum here, for example, if I have 3 and -1, so -1 would never be a maximum later on, so I would remove it. So what I will do is that I will get the front element. First, I will remove the elements from the front deque that are out of this the deque. For example, on this window, I will not use the elements that are, for example, if I'm here, I will not use the element 1, so I would remove it if it's in the deque. So what I will do that every time that I'm in the front element will contain the maximum element of the previous window. So I got the front, so here we have the index in the array, and the index, the first element in the deque, contains the maximum. So bi minus w. Why bi minus w? Because here I is equal to w equal to 2, so bi minus w minus the windows 3, sorry, so it's equal to b0. So the first window, the maximum of the first window is of index 0. So I will remove the elements from rear and from the front. So the element that I should remove from the rear are those that are minimum and are smaller than the elements that I want to add. So as long as, again, is not empty, so let me copy all this because it's the same. So as long as the deque is not empty and we have a rear element and the element that I want to add is bigger, I will delete the rear. Again, I will delete some of the front element. Why? Because they are not anymore in this window. So if we have front Q and we have here E is less than, so the index in the deque is less than or equal than I minus W. It means that it's out of the, so it's before the window that I'm working in, so I will delete the front elements. So at the end, when I finished this everything, so I will keep one element in the deque, so it's the front of QE. I will get it and place it into the deque. So here we have B n minus W, because it's the last element, is equal to A of E. So, and this is it. No, we have forgotten to insert the elements. So as above, we need to insert each index in the deque. So let's run it now. So 3, 3, 5, 5, 6, 7. So it's the same output. So let me repeat again. So in the sliding window, for the first 3 elements, we have just made a special treatment for those. So we would like to add these elements into the deque. However, we will not add all the elements because we need the maximum. So whenever we are inserting elements, so if it's a maximum, if the newest added element is a maximum, so I will remove the elements from the back of the queue. If it's a minimum, I will keep it, because later on when I'm removing the elements from the front of the queue, it may become the maximum element. So this is just for the first 3, and then for the remaining, for each element I will insert it at the end of the rear, but before that I could remove some element either from the rear or from the front. I will remove elements from the front if the index in the deque of the element is before the sliding window, so I will remove those elements, and again in the rear I will do the same as I have done. So if I have a maximum element, I will remove all the rear elements. However, if I have a minimum element which is less than the last rear element, I will keep that, because later on it could be the maximum. So this is it for the exercise. It's not an easy exercise. You can try to solve it for example using arrays. However, let's check the complexity. So we have, for example, n elements in the array, and the complexity should be in terms of n and maybe w. So here we have treated 3 elements, and we have looped 3 times. So in this for we have while. So the worst case is that for each element it will be removed once. So in all this code, if you look carefully, if I have n elements, I will push these elements n times, and then I will remove these elements n times. It can be removed more than times, and just inserting here and here. So the insertion is on I. I'm always inserting the index I. I can remove those elements from time to time. So I have n insertion, n deletion if it's in the rear or in the queue. However, I have here some tests. So the test also, it costs. Whenever the queue is empty, I should find the rear and then do the tests. So the complexity will be around n. It's a very efficient algorithm. And again, thanks for watching. If you have any questions, do not hesitate to write to me, and do not forget to subscribe to my channel and to hit the bell icon to receive all the notification. And again, thanks for watching.